Ready? And shake, 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 shake. Shake your questions. Shake your questions. Woohoo! I don't want to turn it upside down because then they'll fall out unless I have my head covered in it.
Let go.
All right, here we go. First question from the pile is, can you explain valence electrons and balancing redox ionic reactions? Hey, no fair, that's two questions. Yes, I can explain both.
Rule them both out.
Okay. Here's what valence electrons are all about. Take a look at the symbol of any element on the periodic table. For example, calcium. There's a whole bunch of stuff that calcium has. For example, there's a +2 up in the corner. There's a 40.08, whatever it is, up in that corner. There's a little 20 down here, and then down here we have 2882. This represents the electron configuration for calcium. The valence electrons are the electrons in the outermost energy level. These are the ones that are lost or gained during chemical bonding. In the case of a metal like calcium, you notice it has a +2 charge. The +2 means that these two negative electrons are lost when a calcium ion is formed. And the ion has a stable octet, like all ions do. So the purpose of forming an ion is to make a stable octet and get rid of those valence electrons. So that's the deal with valence electrons. If you're going to do it as a dot diagram, you would put the valence electrons as dots around the symbol. 1 valence electron, 2, 3, 4, 5, 6, 7, and 8. As far as the balancing redox ionic reactions is concerned, check this out. If you've got a reaction like, let's say, Fe plus Ca plus 2 forms Fe plus 3 plus Ca, you might look at this and say, hey, wait a minute, this is balanced. I've got one iron on the left, I got one iron on the right, I got one calcium on the left, I got one calcium on the right, but that's not balanced because there are 3 laws of conservation. The law of conservation of mass, which says you have to have the same amount of stuff on both sides. You can't destroy matter, you can't create it. The law of conservation of energy, which says you can't create energy or destroy it, and that doesn't really apply here because energy is not part of this. And the law of conservation of charge, that says the total charge on both sides of the equation have to add up to the same thing. Well, we got +2 on this side, we got +3 on that side, so the charge isn't balanced. So the way we deal with that is we write the half reactions. Fe starts off having no charge, and it ends up being +3 by losing 3 electrons. And then the calcium, which is +2, takes up 2 electrons on its way to having no charge. Now, when you're balanced, you have to have the same number of electrons lost as you have gained. And we don't have that here. Iron loses 3, but calcium only gains 2. So we have to make it so that they're both lost and gained the same number of electrons. And the way we do that is we cross-multiply them by each other's number of electrons. I mean, it's kind of like finding the lowest common denominator. What's 3 times 2? So when we're done, we want there to be 6 electrons lost and 6 electrons gained. To do that, we multiply the iron by 2, because 2 times 3 equals 6. That means we're going to have 2 Fe zeros and 2 Fe plus 3s. And we're going to multiply the calcium by 3, because 3 times 2 is 6. So we'll have 3 calcium plus 2s and 3 calcium zeros. Let's just make sure it's balanced both on charge and mass. We have 2 irons on the left, 2 irons on the right. That's cool. 3 calciums on the left, 3 calciums on the right. That's good. We have a total charge of 3 times +2 is +6 on this side, and 2 times +3 is +6 on that side. So it's balanced both for mass and for charge. And that's how you balance an ionic reaction. If they've removed the spectator ions, it makes it a little bit more difficult to balance it, but absolutely not impossible. Does anybody have any questions further on this before I move on to the next question? Go ahead.
When it comes to the anode and cathode, right? Oxidation is anode, right?
And this would take place. So if we set this up as a battery, if we used an iron electrode and a calcium electrode, and we put this in some, let's say, iron nitrate, iron 3 nitrate, and we put this in some calcium nitrate, and we connected it with ye olde salt bridge, connected these with a wire through a load. The iron is losing electrons, the calcium is gaining. Now this wouldn't work. Anybody would look at this and say, wait, this isn't going to work, because in a redox reaction, if you take a look at reference table J, on reference table J, calcium is listed higher than iron. So this reaction will not be spontaneous. You wouldn't be able to use this to make a battery. But if you could, that would be the anode and that would be the cathode, because the iron is losing the electrons and the calcium is gaining them. This would be an example of a non-spontaneous redox reaction. Okay. Again, based on the positioning on reference table J. Anything else based on this?
Nope.
No? Cool.
Next question.
Next question. Next question. How much wood could a woodchuck chuck if a woodchuck could chuck wood? 7.
Somebody wrote that?
No, but seriously, can you go over radioactivity? Yes, I can. I can definitely go over radioactivity. There, I went over radioactivity.
Touche.
When you've got an atom, the atom has 2 particles in the nucleus, the protons and the neutrons. For example, let's say we have carbon. Carbon comes in many different forms. Let's take a look at the 2 that we deal with most often, carbon-12 and carbon-14. They're both carbon because they have the same number of protons, but they have a different number of neutrons. The proportion between protons and neutrons can make an atom either stable, if it's close to a 1-to-1 ratio, especially for small nuclei, but if there's too many neutrons compared to protons, or the other way around, the nucleus can become unstable and vomit out pieces of itself until the ratio gets back to a reasonable proportion. We called it earlier this year, if you want to do the proportion between protons and neutrons, if this is a 1-to-1 ratio, then small atoms tend to be stable around a 1-to-1 ratio. But as the nucleus gets bigger, the zone of stability tends to move in the direction of excess neutrons. But past a certain point, element 83, past that point, every single isotope is going to be radioactive. Smaller elements can also be radioactive if their isotopes are outside the zone of stability. If there are too many neutrons, then what happens is a neutron is turned into a proton. And the way this happens is with beta decay. If there's too many protons, then a proton gets turned into a neutron. This happens through positron decay. And if the nucleus is just too big, it starts to fall apart by vomiting out large pieces of itself, 4/2He, which is alpha decay. So that's why some things undergo radioactive decay. Either the nucleus is just too big to stay together, or there's too many neutrons, or there's too many protons. Now if you take a look at reference table N, that's N as in, no, where did I put it? Reference table N. There's a list of selected radioactive isotopes on reference table N and the way that they decay. Hip hip hooray. So if we take, for example, let's say, oh dear, just give me one of them, any one of them.
Calcium.
Calcium 37, sure. 37Ca undergoes, according to this table, positron decay, beta positive. Now, before you can really move any further with this, we've got to find out some more information about calcium. Namely, what its atomic number is. So calcium has an atomic number of 20. And then if you don't remember what a beta positive particle is, you can just look it up on reference table O, where it says 0 positive 1e. And then again, remember the law of conservation of mass and the law of conservation of charge. We have 37 as a mass on the left side. We need 37 total on the right side, so the mass of our decay particle is 37. We have a total charge of plus 20 on this side from the 20 protons. We have a total charge of plus 1 on this side. How many protons do we need to make this work out?
21?
21 and positive 1 will end up being 22.
20.
19.
19.
19 and positive 1 adds up to 20. Now, of course, since the atomic number changed, that changes what element you have to potassium. All right, that changes it to potassium. Let's pick something else. Let's say beta decay. What undergoes beta decay here? Hydrogen 3. Yep, 3 hydrogen undergoes beta decay. And again, we need to look up the atomic number for hydrogen, which is 1. And according to reference table O, a beta particle is 0, -1 e. So we've got 3 on the mass side for the left. We need 3 total for the right, so what mass do we need over there? 2?
Wait, 3.
3.
That's why I'm at the bottom.
Right, the atomic number, you're right. We do need 2 for that. Now here's where it comes in. See, 2 and -1 adds up to 1. And it's 1 on the other side.
Okay.
And then we look up element 2, helium. So that's how natural radioactive decay works. You have a nucleus which is unstable because it either has too many protons or too many neutrons, or is just too big, and it vomits out pieces of itself to come back to a more stable ratio between protons and neutrons. A nuclide basically just means this, the symbol with the mass and charge.
Oh. Oh, okay.
We could also call this K19 to represent that it has a mass of 19. Hello. Wrong! Edit that. K37, because the mass is the number that comes after the dash. Yeah. What? This is what we call editing.
Dude, are you gonna like edit some of the stuff out of it?
I always edit it for time.
Next question.
I won't edit that. Third question.
You gonna edit that out?
What is the difference between fusion and fission? Fusion and fission. What is the difference between fusion and fission? Okay. I want you to think about this. Where are you? Here we go. Think of this as being a nucleus. I know it looks like silly putty, but just pretend. Fission is when a nucleus is split apart into 2 smaller pieces. If you think from biology, binary fission was taking a cell and dividing it into 2 cells. That's what fission is. Fusion is when you take 2 small nuclei, right, and you fuse them together under enormous temperatures and pressures to make big nuclei. And that's really the only difference between fission and fusion. Fission is when you take a big nucleus like uranium, 235, and split it into barium and krypton. That would be fission. Fusion is where hydrogen is built into helium at a temperature of millions of degrees. And that's the difference between fission and fusion. Yeah?
Can you show us our equations?
Yes, I can. If you take a simple look at, let's say, this one right here. 2, that's not a 2. Well, it has a 2 in it. Okay. 2,1H plus 2,1H forms 4/2He. What would that be?
Fusion.
That'd be fusion, because you're fusing 2 nuclei together to make 1 new nucleus. But if we have, let's say, 235/92U being hit with a neutron and splitting into barium and krypton, the numbers elude me for the moment, then 3 more neutrons are thrown off. If you're taking 1 nucleus and splitting it into 2, that would be an example of fission, right? For some reason the numbers elude me for the moment. Oh, nope, almost had them. Can you go over the history of electrons around the atom, such as the theories of what scientists believe the atoms to look like? The history of atomic structure. In the beginning were the 2 Greeks, Democritus and Leucippus, who were sitting around drinking wine, getting drunk, eating grapes, and one of them said, "Hey, if I take this grape and cut it in half, I'll have half a grape. But if I keep cutting it in half and 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 keep cutting it in half, eventually I'm going to get to the smallest piece that still retains grapeness. And we can't divide it any further because then it wouldn't be a grape anymore. And we call that particle atomos, which means indivisible, which is where we get our name atom from. Then fast forward to the 1800s, where a guy named John Dalton did some work with newly discovered elements hydrogen and oxygen, and discovered that when you take water and decompose it and you weigh the hydrogen and oxygen, you always get the same proportion by mass of hydrogen to oxygen. And he decomposed other compounds, and he found this to be true of all compounds. So he came up with the concept of atomic mass, and his idea of an atom was a solid indestructible sphere, every element's mass having a different mass. He didn't really have any other picture to prove this or anything, he just said, oh, solid indestructible sphere. Then along comes a guy named J.J. Thomson and his cathode ray tube, and he tested the charge of electrons and found them to be negative. And he realized the atom isn't solid and indestructible, they're actually pieces you can pull off. We'll call those electrons. And the rest of the atom is something that's positive. We really have no idea what that is. Then along comes this guy named Ernest Rutherford, who shot alpha particles at gold foil. Most of the alpha particles went right through the gold foil, proving that the atom is mostly made of empty space. But a few, about 1 in every 10, 20,000 of them would bounce off, indicating that there was something small, dense, and positive in the middle, which we refer to as the nucleus. Then along comes Niels Bohr and says, yes, I like this idea of electrons around the nucleus, but they occupy definite energy levels. Because when you take an atom and you excite it, woohoo, the electrons rise up in energy level, and when they fall back down, they always release the same colors of light, giving us the bright line spectra. And then they added quantum mechanics in there when they discovered things like sublevels and orbitals, an orbital being the place where you're most specifically going to find an electron, a region of space where the electron is most likely to be found. And that's still the best model that we have. I mean, they've got some other exotic things out there called string theory, which says that if you're walking with your shoelaces untied, you're going to trip on the string and fall. That's not really what it says, but anyway, it's just not even really a theory because they've never been able to substantiate it. Okay, any other questions based on that? All right, a couple thousand years worth of time compressed down to about 3 minutes. All right, next question. What is heat of decomposition? There's really no such thing that we've done this year called heat of decomposition, but if you were to talk about that, let's talk about heat of reaction, because decomposition is a type of reaction. If you do a chemical reaction where, let's say you start with a certain amount of energy, we call that heat of reactants. And the products that we form have a certain amount of energy that we call heat of products. And it takes a certain amount of energy to get the reaction to the point where it can start. Heat of activated complex, and it takes activation energy to get there. You're going to start with heat of reactants, give it the activation energy to get started, and then new bonds form and the products are formed. The heat of reaction, if decomposition is your reaction, then we'd call it heat of decomposition. The heat of because if you do synthesis, it's called heat of formation. So if you break it up, it would be called heat of decomposition. That would be a good term for it. This value here, which what do we call that all year? Delta H. That is the heat of reaction. The total change in heat from start to finish. So if we started at 50 kilojoules and we ended at 10 kilojoules, our heat of reaction would be negative 40 kilojoules. We went down by 40. The negative indicates a downward direction in the amount of heat. And that's what heat of decomposition would be if we were drawing this for a decomposition reaction. Of course, most decomposition reactions are endothermic, and I drew one that's exothermic, but well. Next one. What is the difference between heat of vaporization and heat of fusion? And then it gives me a Twitter feed.
Follow it?
These are supposed to be anonymous.
What?
That means I can only marry one person? No, it's monogamous. All right. What is the difference between heat of vaporization and heat of fusion? Good point. Good question. Here's how it works.
Yeah, Jack.
I got it too quick? Did I erase it too quick?
No.
Okay.
It's on the.
It's on the video, yeah.
Onto the shadow.
Okay, here's the way it works. Temperature versus time. We're gonna take a sample of solid and heat it up. And as you add heat to a solid, the temperature gradually rises until it starts to melt. What happens to the temperature as a substance undergoes a phase change? Stays the same until the phase change is done. Then once all the solid has been melted, the temperature of the liquid rises until you hit the boiling point, at which point the temperature stays constant again until the boiling is completely done. Then the temperature rises once more. Now, usually we say if we want to find out how many joules it takes of heat to make a change happen, we usually say Q equals mc delta T. But this assumes that your temperature is changing. So we can only use Q equals mc delta T while there's a change in temperature. As the temperature is changing, just take how much stuff you're heating up times the specific heat times whatever temperature change you get. But during a phase change, you don't have a temperature change. But it still takes heat to melt stuff. I mean, in the wintertime, if you've got ice on your windshield, you have to turn your defroster on. And the heat from that melts the ice. So what we need to do is have a similar equation, except without the delta T in it. And that's where heat of fusion and heat of vaporization come in. For melting, we use Q equals mass times heat of fusion. And the heat of fusion of water is something very nice. Take away 334 joules per gram, and what you get is ice. It's different for every substance. For water, it's 334. When you boil, you need Q equals mass times heat of vaporization, because it takes a different amount of energy to break the attractive forces between the liquid than it does to break the attractive forces between a solid. See, the way it works is this. Solids have very strong attractive forces. Gases have none. When you turn a solid into a liquid, the liquid molecules still hang out together. They're in a solid crystal lattice. So what you're doing when you're turning a solid into a liquid is you're only weakening the attractive forces. You're not getting rid of them altogether. You're only weakening them enough so that the molecules can flow past each other. And it takes a certain amount of heat to do that. But when you turn a liquid into a gas, what you're doing is you're eliminating all the remaining attractive forces. You're breaking every attractive force between every molecule and letting every molecule of gas go every which way completely unattracted. The heat of vaporization for water is 2,260 joules per gram, significantly higher than the heat of fusion. Because in the heat of fusion, you're only weakening the attractive forces. Heat of vaporization, you're completely eliminating the attractive forces. So it takes a lot more heat to get the molecules to move fast enough to do that. And that's the difference between heat of vaporization and heat of fusion. Is that what you were looking for?
Yeah.
Sweet. Okay, I'm going to shove this over to the other side. So if you want to copy it, it'll still be there. Okay, next question. What's the difference between a heterogeneous and homogeneous mixture? Excellent question. This iced tea, being transparent, is homogeneous. And what that means is that all the particles in this mixture are evenly dispersed throughout the entire mixture. If I was to take a little sample here and compare it to another sample over here, the composition would be identical. You'd have the same concentration, you'd have the same stuff. It's homogeneous. Heterogeneous is a chunky mixture. When you take a look at it and say, okay, here's part of a mixture over here, it's different than the part of the mixture over here. A beach would be an example of a heterogeneous mixture. You're walking, okay, there's sand, but there's some pebbles over there, but not over there, and look, there's a crab over there, and there's a dead fish, and there's a hypodermic needle over there. And, you know, the composition is different depending on where on the beach you are and when in the 21st century you happen to be and where on the planet you are. So that's a difference between homogeneous and heterogeneous. Homogeneous means it's the same composition throughout the whole sample, consistent composition, where heterogeneous is sort of chunky. It's different from place to place. Kind of like if you take muddy water and shake it up, it may look homogeneous for a little while, but you go down to the atomic level and hey, here's some water, big chunk of mud! You know, it's heterogeneous, it's chunky. If it's not evenly mixed right down to the molecular level, it's not homogeneous. Next question. Did Schrodinger's cat live? Yes, no. Next question.
That was a stupid question. Jason.
What is natural decay? We've already tackled that. What does both nuclear fission and fusion do? We've already tackled, we haven't tackled what they do. All right, let's talk about nuclear fission and fusion. We've seen what they are. Now let's take a look at what we use them for. Nuclear fission, which uses uranium-235, nuclear fission takes uranium and splits it into two smaller nuclei. This gives off a lot of energy. E equals mc squared says that anytime you have a nuclear reaction, you lose a tiny bit of mass and it's converted into a whole lot of energy. Fission produces thousands of times more heat than burning fossil fuels do. So you only need about 1/1000th the amount of stuff to get the job done. So nuclear fission is a very efficient way of generating the heat that turns the turbine, which turns the magnet inside the coil of wire, which makes your electrical current. Just like a lot of you got zapped earlier on in the year. Okay? So that's what fission does. It produces electricity for us by fission reactions. Nuclear fusion, the only application we've ever had for it is nuclear bombs. But we're currently working on ways of harnessing nuclear fusion power, which generates thousands of times more energy than fission does, and uses hydrogen as a fuel, which is the most common element in the universe. So if we're somehow able to harness the power of fusion to generate our power, then we're golden forever, pretty much, because the fuel for fusion is what powers the stars. In addition to that, it says, how do you do coefficients? To do a coefficient, you simply write a number in front, and I'm assuming that what we're talking about here is balancing. So I'll show you an example of a balanced reaction. Let's suppose we have Fe, and we're going to react it with some diatomic oxygen to make iron 3 oxide, Fe3O2. Okay? Again, the law of conservation of mass says you have to have the same amount of stuff on both sides. Now, according to this reaction, it's not an equation yet, because equation means it's balanced. This is a reaction, and it hasn't been balanced yet, so we can't call it an equation yet. Because equation means equate, equal, same amount of stuff on both sides. So how many irons on the left?
1.
We only have 1, but how many on the right?
3.
This is where we use a coefficient. We put the number in front to balance it so that there's the same amount of stuff on both sides. How many O's on the left?
1. Oh wait, 2.
2. And how many O's on the right?
2.
So this equation is now, well, now it is an equation, because we have the same number of irons on both sides and the same number of oxygens on both sides. And that's how this works. Now, let's say, instead of this, I had Fe plus Cl2 forms FeCl3. When we start out, we look at it and say, hey, there's 1 iron on the left, 1 iron on the right, so far we're good. But we have 2 chlorines on the left and 3 chlorines on the right. So now what we got to do is we got to get the lowest common denominator. 2 and 3, multiply them together, what do you get?
6.
So 2 times 3 is 6. So we put the 3 in front as a coefficient. 3 times 2 is 6. So now we have 6 chlorines on that side. And we have to revise the iron to put a 2 in front of it. The importance of balancing is to remember that the numbers go in front as coefficients. You don't actually change the subscript to balance it. You only use coefficients. Other here too, what is an ion exchange reaction? Okay, here's the deal behind that. There's more than just one question out here. What I'll do is I'll answer this question, and then I'll keep this in reserve and come back to it, and I'll answer other questions as we go along.
Wonder it's
Well, it's because somebody had a lot of questions.
against the rules.
I don't care.
Alright.
You know, it's better than who is Superman's real identity.
Someone wrote that?
No. Okay, here's an ion exchange reaction. Let's take sodium chloride and silver nitrate. If you take a look at reference table F, you'll notice that all sodium compounds are soluble. So we're going to take sodium chloride and dissolve it in water. And we're going to take silver nitrate. Nitrates are always soluble, so again, it's soluble in water. When you react the 2 of them, you get an exchange of ions. It's kind of like, you know, where you have the sodium is positive bond to the negative chloride, positive silver bonded to the negative nitrate. And what happens is the ions switch who they're dancing with. It's kind of like a little chemical square dance. Sodium's dancing with chlorine. It's like, hey, I want to dance with nitrate. So the sodium and nitrate will come together. Now, how do we know it's sodium and nitrate that'll come together and not sodium and silver?
They have to go on opposite ends of it.
Right, opposite charges attract. Like charges repel. You'll never catch sodium dancing with silver because positive and positive repel. Only opposite charges attract. So that's the first exchange. Sodium goes off with nitrate, leaving silver and chloride to go off together. The entire purpose of this reaction, chloride is usually soluble. Silver is an exception to that, making silver chloride a precipitate that falls out of solution. And that's the whole purpose of an ion exchange reaction, to produce this precipitate. The silver in this solution and the chlorine in this solution fall deeply and madly in love and leave the dance floor, leaving sodium and nitrate to say, what happened? Okay, I'll save the rest of this for a little while. Let me pull out another question.
Goldman Sachs.
Goldman Sachs. Balancing a reaction.
Did it.
We've already done it. Woohoo! I had a feeling we were going to get duplicates, which is cool. Okay. How to find molarity? Excellent question.
Thank you.
Take a look at reference table T. That's T as in, there are the equations. T. And you'll see that it says molarity equals moles divided by liters. So let's look at that. Bum-ba-da-bum, bum-ba-dum, bum-ba-da-bum, bum-ba-da-bum. Oh my gosh, it's going up on YouTube. I'm going to have to pay royalties. Otherwise, Indiana Jones might come to my house and beat me up. All right. Molarity equals moles divided by liters. In other words, right here I have a 1 liter container. If I had it filled up all the way with solution, if there was 1 mole of stuff dissolved in it, it would be a 1 molar solution. If I had 3 moles of stuff dissolved in it, it would be a 3 molar solution. So let's say I have 2 moles of stuff. Let's say 2 moles of sodium chloride dissolved in 4.0 liters of solution. Then all you got to do is plug and chug. We've got 2 moles divided by 4.0 liters of solution. What's 2 divided by 4? Half, or 0.5. And because there's only 1 sig fig in the top number and 2 sig figs in the bottom, we stay with our 1 sig fig. If this had been 2.0, then what would we round to? 0.50, right. Molar. It's not always this easy though. Sometimes they'll say we have 20.0 grams of NaCl dissolved in 400 milliliters of solution. Then you got a little bit of work to do, because in order to get moles, you got to convert grams to moles. And how do you do that?
The equation.
How do you convert grams to moles?
The equation.
What equation?
So 1 number.
Mole calculations. Number of moles equals given mass divided by gram formula mass. So how do we get the formula mass of sodium chloride?
The mass of sodium and chloride.
Okay, the sodium has a mass of 23.0. 23.0. Chlorine is 35.5. Add them up and you get 58.5 grams per mole. Divided out to cancel out grams. 20 divided by 58.5. Alright, how many sig figs are we going to report that to?
3.
Alright, so 0.342. 342 moles. Alright, now let's deal with the milliliters. How many liters is 400 milliliters?
Mole.
Divided by what to convert milliliter? 1,000. So that gives us 0.400 liters. And then we just pop in 0.342 divided by 0.400 is 0.855 molar. And that's how we calculate molarity. It's different if you've got MAVA equals MUBVUB. If you got the molarity of an acid, you're trying to find the molarity of the base. That
Can we do
requires
that?
something different. What's that?
Can you just give us like an example? Of
Yeah, you want an example of that? Yeah, all right. 20 milliliters of 0.100 molar HCl neutralizes how many milliliters of, I don't know,
Redox.
0.300 molar NaOH. Now, because we've got an acid and a base, now we use MAVA equals MUBVUB. MAVA equals MUBVUB. We're trying to solve for how many milliliters of the base. Divide both sides by molarity of base and plug it in. Molarity of acid, 0.100 molar. Volume of the acid, 20 decimal point milliliters.
Jesus.
No, over the molarity of the base, 0.300. Molarity cancels and you just solve it through. So if you're asked to calculate for molarity, if they only give you like moles in liters, then you just use moles per liter. But if they're giving you an acid and a base, you have to use MAVA equals MUBVUB. You have no other choice. Okay, let's take another one from this list. What is a redox reaction? There are 3 examples of a redox reaction that we've done. 3 examples of a redox reaction. All right. First, synthesis, where 2 elements combine to form a compound. The opposite of that, decomposition, where a compound is broken up into its original elements. And single replacement, where an element replaces another that's already in a compound. The reason they're considered redox, which is short for reduction-oxidation reactions, is because the element that's by itself, when it goes into a compound, ends up with a charge. In this case, it's oxidized. The other element that goes into the compound is reduced. That's why it's called a redox reaction. Same deal here. Elements are charged in a compound, they're not charged when they're by themselves. A plus was reduced, B minus was oxidized. In single replacement, A was by itself, now it's in a compound, it was oxidized. B was in a compound, now it's by itself, it was reduced. Well, C sits on its big fat pimply butt just watching, making it a spectator ion. You can tell if a reaction is a redox reaction very simply. If an element is by itself on one side of the reaction, but then in a compound on the other side, you know its charge must have changed. That means reduction and oxidation have taken place. So that's the #1 clue to determining whether it's a redox reaction. If it's an element on one side, and if it's in a compound on the other, you know that it's undergone oxidation or reduction. Okay, another one from the pile. How do you figure out the oxidation and reduction state of a chemical when given a balanced equation representing a reaction? We've kind of just done that, but I'm going to show you something that's related to it. KClO3. Let's find the charge of every single element in this compound. First of all, K. +1 is the only charge it has listed. +1 it is. Chlorine has charges that are possible are -1, +1, +3, +5, +7. We'll come back to it. Oxygen, the only charge it has listed is -2. Chlorine has to be whatever it takes for all these charges to add up to 0. So we've got +1 for the K. Guys, what's the total charge of oxygen here in this compound? -6. So what does Cl have to be to make this all add up to 0? Positive 5. And that's how to find the charge of any element in the compound. The periodic table is the best. And if the element is by itself, what's its charge? 0, right. It's got the same number of protons and electrons, so it hasn't gained or lost any electrons. Okay, next one. There's a little drawing here with somebody's name next to it. I wonder whose this is.
Can we see it?
Please go over a PE diagram. I never quite got that. Now, we've already gone over a PE diagram, but I'll do another one. Okay. All right. Whoa, hello. In a chemical reaction, there are two separate yet equal groups. No, that's Law and Order. All right. Where was I? Before I was so rudely. Oh yeah, go over PE diagram. All right. You have reactants, and they turn into products. And each of these has a certain amount of energy associated with them. Let's suppose that stored in the chemical bonds of the reactants, we have 50 kilojoules. And stored in the chemical bonds of the products, we have 20 kilojoules. Now, according to the law of conservation of energy, you can't gain energy, you can't lose it. So how much energy must have been lost?
30.
And we need to put it on this side to keep the law of conservation of energy working. 50 total kilojoules on this side, 50 total kilojoules on this side. If we graph, exactly, exothermic. If we graph it, potential energy versus time, reaction coordinate, we're going to find that we start out with 50 kilojoules. We end with 20, and we call these the heat of reactant and the heat of product. It always takes energy to get a reaction to start. If you remember from yesterday, with these loud, obnoxious things right here, if I take one of these and just drop it from a short height, it's not going to apply enough energy to go. What happened?
Get the zapper. Show the YouTubers.
Not worried about it, they don't eat much. But if I put plenty of energy into this,
Try to hit a view with one of
that
those.
sucked.
Imagine. Throw it at the beat. He's gonna angry.
Yeah, right.
That'd be
It's
awesome.
going to hit with enough force.
He's on
Where
that
is it?
poster right there. Oh, throw it at him. Throw it.
Well, maybe it'll go out the window. Let's try this one. Ready? And... Ha-ha! Let's map out what just happened. At the moment of impact, I applied a force to it we call activation energy. That brought us up to a level called heat of activated complex. Then you saw the flash. The flash was all of that energy being released to form the products, giving us a negative change in heat, a negative heat of reaction. And that's the way a potential energy diagram works. It maps from start to finish what happens to energy in a reaction. We added energy to break bonds, and then new bonds formed, releasing energy. And that's a PE diagram. Okay, back to this one here. What is titration? The MAVA equals MUVA question that I gave as an example is titration. It's the controlled neutralization of an acid and a base. MAVA equals MUVA. Next question. How do you figure out how to do the empirical formula? Okay, empirical formula. The empirical formula is the one that has been sanctioned by the Empire, and the rebellion has been struggling hard to free the rest of the galaxy from the tyranny of the empirical formula. And every time you see the empirical formula, you actually hear music playing, dun dun da da dun da da dun da da.
Star Wars.
What?
The beat.
Oh, jeez.
You're gonna get sued, Jack Knight.
Yeah, I'll get sued. I don't really care. Okay. I didn't mean that. All right, let's see. How do you figure out the empirical formula? Let's say we have a formula of N2O4. What this tells us is we have a molecule with 2 atoms of nitrogen in it and 4 atoms of oxygen. The empirical formula is the ratio between them, simplified. Simplify this down, what do you get?
Nope.
NO2. If you divide these both by 2, the empirical formula is NO2. The empirical formula is the simplest whole number ratio between the elements in a compound.
So, the reason why do you like divide by 2? Like
Because that's the lowest common denominator between them. If I gave you, let's say for example, C8H18, what's the lowest common denominator between those two? If you divide that by 8, no, 18 is not divisible by 4 or 8, but it is divisible by 2. If you divide them by the thing that they can be divided by, you get C4H9. That's the empirical formula. What's wrong?
Also, the smallest could be.
Right, exactly. Just the lowest possible ratio between the atoms in the compound. That's the empirical formula. Okay. Next up. Running out of slips here. What is decomposition? How do you know it is decomposed? We've just talked about decomposition and what it is. And it also says, how do you know covalent, ionic, or bonding? Okay. Here's bonding in a nutshell. When two atoms bond with each other, there's a difference in their electronegativity. You can look this up on reference table S. It's the attraction that an atom has for electrons in a chemical bond. And depending on who has a greater attraction for electrons will determine what kind of bond you have. It's a scale that goes between 0 to about 3.5. And excuse me just a second, let me get that phone. Anyway, so we have this scale between 0 and 3.5. At a difference of about 1.7 is the cutoff between being able to share electrons and transferring electrons. Between 0 and 0.7, the difference in pull is not strong enough for electrons to be transferred. So valence electrons are shared. For example, H has one valence. Try that again. H doesn't look like an X. H has one valence electron. Another H has one valence electron. That's a covalent bond. H has one valence electron. Cl has 7, but only one unpaired valence electron. So they share electrons. This has an END of 0 because they're going to be the same element. H and Cl are a difference of 1.0. Once you get past 1.7, valence electrons are transferred from a metal to a non-metal. For example, sodium has 1 valence electron. Chlorine has 7. Sodium has an electronegativity of what? Sodium! Where are you? There you are. 0.9. Chlorine is 3.2. This gives us a difference of 2.3. That's greater than 1.7, in case you were wondering. So what happens is, sodium loses its valence electron. It gets transferred over to chlorine. Sodium becomes a positive ion. Chloride is a negative ion, and these oppositely charged ions attract. So you can see the difference. In covalent bonds, the electrons are being shared. In an ionic bond, there is no sharing. There's just attraction of oppositely charged things for each other. This is a covalent bond, and this is an ionic bond. Now there's a couple of different, yes?
Oh, I was going to ask at what point do covalent bonds become non-polar?
Boom! The lower the difference in electronegativity, the less polar the molecule is. And when you get to a difference of about 0.4, that's when you end up with a non-polar covalent bond. just like in H2. A difference that's between 0.4 and 1.7, that would be a polar covalent bond, like this bond here between H and Cl. And that essentially is all there is to bonding. If the difference in pull on electrons is not great enough, then the elements just have to simply share their unpaired valence electrons. But as the difference exceeds a certain point, the metal, the less electronegative atom, has no choice but to transfer its electrons over to the more electronegative atom. Okay. And that's bonding in about 4 minutes. Yeah?
What's the difference between nonpolar and polar?
The difference between polar and nonpolar really reveals itself when you look at the whole molecule. For example, no matter what you do, this molecule is going to be a nonpolar molecule because there's completely even sharing of electrons. If you take a look at, let's say, a water molecule, this bond is polar, oxygen wants electrons more. This bond is polar, oxygen wants electrons more. That gives this molecule a not symmetrical distribution of electrons, leaving the oxygen side partially negative and the hydrogen side partially positive. This will allow the water molecule to attract other water molecules, or ions, which is why stuff dissolves in water, because the oppositely charged ends of water molecules are attracted to oppositely charged ions and can keep them apart in a solution. So the polarity of a bond contributes to the polarity of the entire molecule. There are situations where you can have a polar molecule, a polar bond, and yet the molecule be nonpolar. For example, in carbon dioxide, this bond is polar, but these bonds are also polar. This bond is polar in the direction of oxygen. This bond is polar, but also in the direction of oxygen. These two cancel each other out, leaving the whole molecule nonpolar. So the polarities of the molecule, polarities of the bond combine to determine the polarity of the whole molecule. Yep. Okay, next question. What is saponification? Saponification is the manufacture of soap by taking fat, reacting it with a strong base, and soap is one of the products that you form from that. It goes into more detail than that, but that's really as far as you need to know for the Regents. I hate to say that, but we're kind of pressed for time. Yes, sir?
What's fermentation?
Fermentation is the production of alcohol by taking sugar and digesting it with yeast.
Okay.
And carbon dioxide is made as a byproduct. Okay, here's the next question. How can you tell if a metal is in the liquid phase at STP? There's two ways of remembering this. One, there is only one metal that's a liquid at standard temperature and pressure, and that's mercury. The only other element that's a liquid at STP is bromine, but that's a nonmetal. The other way you can tell is to go to reference table S and look up the melting point. If the melting point is below 273, then you know it's a liquid, as long as the boiling point is above 273. So that's how you can tell which metal is a liquid.
Wait, if it's higher.
If your temperature, STP, is 273, okay? If the melting point is below that, that means that at 273 it's going to be a liquid, as long as the boiling point is above 273, because this is where it's going to be a liquid.
Okay.
But you can also just remember that mercury is the only liquid metal at STP. You only have to raise the temperature a few degrees and other things start to melt, like gallium is a pretty low melting point metal too. Okay, next question, and we're running out, which is good because we're running out of time. Could you remind me about the Bronsted-Lowry definition of acids and bases? Absolutely, and there's this like smiley face too, which is really cool. Okay. Bronsted-Lowry. Now, the Regents doesn't think you're smart enough to remember the names Bronsted and Lowry. In fact, the only name they ever really mention on a Regents exam is Arrhenius. And the Arrhenius definition of acids and bases said simply that if we have an acid, it contains hydrogen, and a base contains hydroxide. And when you react them, you get water and a salt. That's the Arrhenius definition. Acids have a hydrogen, hydroxide for a base. That's Arrhenius. Bronsted-Lowry gets a little deeper than that. It says if we take NH3 and we react it with H2O, we're going to get H3O plus NH4. No, that's dumb. NH4 plus and OH minus. There we go. Now, what happens to NH3 determines whether it's an acid or a base. Did NH3 gain a hydrogen or lose a hydrogen? Since it gained a hydrogen, by the Bronsted-Lowry definition, that would make it a base. A base is a proton acceptor. Whereas H2O did what?
Lost.
It lost a hydrogen, making it a Bronsted-Lowry acid, a proton donor. Think about this in terms of oxidation and reduction. Oxidation is the loss of electrons. Acid is the loss of hydrogen. Reduction is a gain of electrons. A base is a gain of hydrogens. Basically, it works very similar. And I think we have time for one more question. Can we go over balancing? Okay, we have done that. If you want me to go over anything additional, please come up to me and ask. Can you do some molarity questions? Been there, done that. What is the center of our solar system? How big is the universe? The center of our solar system is the sun. Well, actually, it depends. If you're talking about the gravitational center, it'll be between the sun and Jupiter. And the universe is about 13.7 billion light years across as far as we know. And we've already says difference between ionic and covalent bonding. We've already done that. And I don't know, I don't care. And what are the different types of elements and where on the periodic table? Very good question. Okay. This little zigzaggy line is the dividing line between these guys, which are metals, which lose electrons, and these guys, which are called nonmetals and gain electrons. And in between, we have the...
What?
Non-metal.
In between, we have the metalloids, which sometimes gain and sometimes lose. And then over in group 18, the elements that don't react with doodly squat, noble gases. Those are the kinds of elements and where they're located. And finally, actually there's one more after this. Law of conservation of mass, we've already done that. Through balancing, can't create mass, can't destroy it. And finally, molarity, how do you do it?
Oh.
Do we have to know like alkali metals and alkali earth metals?
The elements in group 1 are called the alkalis. They react in water and are very tiny size. They love to lose electrons when they form a bond of these reactive atoms. I can say I'm rather fond. Group 2 elements, alkyl and earth. 3 through 12, actually 3 through 11, but sometimes they call it 3 through 12, transition elements. And then group 17 are the halogens, which are incredibly reactive, and group 18 are the noble gases. Only elements in groups 1, 2, and 17 can never be found pure in nature, because the second you make them, boom, they're going to react with whatever happens to be around them. Whew! Was that worthwhile?
Yeah.
Do you want to try that again tomorrow?
Yeah.